we'll discuss about case 5. What is case 5? In case 5, the diagram looks like this. So it is the dotted line represents the axis of rotation, and if the rod is position of the rod is like this, means it is the axis of rotation, and this is the length of the rod. This is the length of the rod, L, and mass of the rod is m. Let this distance is d or x, anything you can take. So let this distance is d. The distance from the axis of rotation to the length of rod is d. In this case, now see, this is the distance we see from the beginning to end, or in every position of the rod. The distance of the axis to the rod is same everywhere. This is d, this is again d, this is again d, this is again d. So we can see the distance is same everywhere. So there is no variation of distance, or there is no variation of mass distribution. So in this case, we can replace this rod by a point mass of mass m, and length will be negligible. So in this case, our diagram will be changed. So this is our axis of rotation, and we can replace this rod by a point mass of mass m, and we will not consider the length of the rod in that case, but distance will be same as d. Now this point mass is rotating about an axis about an axis at a distance d from the axis of rotation. If this point is rotating about this axis, then what should be its moment of inertia? This is nothing but the case of a point mass. In that case, the moment of inertia becomes I will be equal to m equal to mass of the point mass, or mass of the rod, m into ds square. Now see what will happen if the rod is aligned by an angular position. Now it is case 6, or case 6. For case 6, the diagram will looks like this. This is our axis of rotation. The dotted line represents the axis of rotation, and our rod is rotating in this manner, what is drawn, and its angle is theta with the axis of rotation. Its angle is theta, and this is the axis of rotation. The rod is rotating about this axis omega. In this case, what will be the moment of inertia of the rod? If the length of the rod is taken as L, and mass of the rod is m, in that case, what will be the moment of inertia? For this situation, what we'll do? We will take a small element in the previous way of thickness dr at a distance, which is the distance at a distance r from the axis. Now see, there is a little bit geometric situation. So this is the mass of this element is dm. Mass of this small element is dm, and we see this is a triangle, and there is an angle theta. So if you reduce this figure for this triangle, we can draw this diagram. So there is the angle theta, this is the length r, and so if this is the angle r, this is, and there are two distances, so this becomes, this distance is r dot, so this becomes r dot. So r dot equal to what? Now see, this is a right angle triangle and it is the hypotenuse, and this is the opposite. So opposite by hypotenuse equal to what? So r divided by, so r dot divided by r becomes what? Sine theta. If r dot, so r dot becomes, so r dot becomes what? R dot becomes r sine theta. Now see, now this, we will consider this r dot, not this r, because this is our axis and this rod is rotating in this orientation, and so our moment of inertia will become I equal to what? I equal to integration of r square dm, and what is our limit? Our limit is from minus L by 2 to plus L by 2. This is the limit of integration. And but this is not r dot, this is not r square, this is r dot square, because we're taking this distance, this r dot distance, not this r. And dm is what? And dm is nothing but mass per unit length, m divided by L into thickness of the, or width of the small length. So dm equal to m by L into dr. So if we calculate this, then I means moment of inertia becomes what? I becomes integration of r dot square. What is r dot square? R dot equal to nothing but r sine theta square multiplied by m divided by L into dr, and its limits is what? Minus L by 2 is lower limit, and upper limit becomes plus L by 2. From this equation, if we simplify this, then I becomes the constant, all the constant terms come outside. So m divided by L come outside, and as there is no changes of angle, so there is no variation of angles about inclination, so angle is fixed here, so we can take theta as constant. If theta is constant, then its sine is also constant, so sine theta is also constant, then we can take sine square theta is also constant, so this sine square theta also come outside. So I becomes m divided by L sine square theta. And what is the integral value again? So our integral value is within integral, that is r square dr, and our limit is minus L by 2 to plus L by 2. So it will become, so I becomes, it means I becomes m divided by L sine square theta, and integration of r square dr is what? Is r cube divided by 3, and what are the limits? And its limit is minus L by 2 is lower limit, and upper limit is what? Plus L by 2. So it becomes, as the 3 is constant, so after calculating it will be m divided by 3L, sine square theta, L divided by m divided by 3L sine square theta, and its upper limit is L by 2 plus L by 2 whole cube minus of minus L by 2 minus L by 2 whole cube. Minus L by 2 whole cube. So I becomes, so its moment of inertia. So its moment of inertia so I becomes m divided by 3L m divided by 3L sin square theta, then L cube divided by 8 plus L cube divided by 8. It becomes I equal to 1 by 12 m divided by L, m divided by L into L cube sin square theta. So it's become L square. So that I becomes 1 by 12 m L square sin square theta. So this is the moment of inertia. This is the moment of inertia for this type of rod.